Didn't quite start yet. I guess it started. Okay, so we're going to work problems because your book is tricky, and I didn't think it gave enough examples. So you have the slides. Just a second, I'm checking my notes. So we're going to work problems. Okay, working problems. This is the first one we're going to work. And remember last time we learned KVL and KCL, right? It turns out that if your certain circuits are better worked as a KVL problem, and certain circuits are worked better as a KCL problem. And so hopefully some of these examples will show you when to use which rule. Okay, so here's the first problem. This one is a loop circuit. You can see everything's in series, right? And so it turns out that series circuits are better, easier analyzed with Kirchhoff's voltage law. Although, you know, technically you could do either one that you want because it still all relates to Ohm's law in the end. So let's analyze this circuit. It says find Vx and Vo in the circuit. So Vx, you can see, is the voltage across the resistor there, and Vo is that. So the book put this plus and minus signs on there. The plus and minus signs you should interpret on these resistors is the orientation that you're putting your multimeter probes. So you should not necessarily say that those are the plus and minus signs that you need to analyze the circuit, because if you do that, you're going to get kind of messed up. So rules kind of generally are the sum of the voltage sources equal the sum of the voltage drops, which is KVL in disguise, right? So KVL, we're going to use KVL because it's a series circuit, or it's one loop. So KVL is the voltage, sum of the voltages around the loop is 0, so it makes sense to do KVL. So I am going to somewhat arbitrarily draw a loop, and so I've made a definition of what direction I'm going to analyze this circuit. And so kind of a rule of thumb, or kind of a guideline to solving these problems, go around, look at the problem, and the voltages you're going to take as they come. So it's a minus 70, and you know over here is going to be a plus, because I hit the minus sign first, and the plus sign first on this one, and there's going to be a plus to Vx. And I know I'm kind of going out of order here, but it's for a reason. And then, so your voltages, you're just going to go around the loop and take the signs as they come. But resistors, as I'm going around the loop, I'm going to establish this convention of always writing plus minus, and I'm going to ignore these other markings on here because this is your measurement marking. This is where you put your red probe and your black probe of your multimeter. So it turns out if I were to measure later on, I'd put my red probe here, the plus one, and my black probe here, and I would get that voltage. But when I report this full voltage, I would be putting the probes in the reverse order, red here and black here, the way it's drawn. So when you're doing KVL, go around and get the voltage sources in the loop, and then, so it's a minus 70, and then put the resistor markings on, always current, this is like a current going into the loop, it's plus, minus, and then go ahead and write current, still going this direction, so plus, minus. It's my convention. The current is going around this way, and every time I hit a resistor, I'm going to write plus, minus, plus, minus. It'll make this problem easy, consistent to solve. So, so it's plus Vx, which is, with Ohm's law, I times 10 ohms, right? Current I in the loop, Ohm's law, V equals IR. Then plus this one, which is what we had, and then plus this resistance, which is also, or this voltage drop, which is I times 5 equals 0. So it's a little bit in different order, but every time I had a resistor, it's going to be a plus term. Okay, so minus 70, Vx by definition is I times 10, right? And this is a voltage controlled source, The voltage here depends on the voltage here. minus 70 plus, make that substitution right here, 2 times I times 10 plus I times 10 plus I times 5 equals 0. So this is an Ohm's law application, this is an Ohm's law application, and this is my voltage controlled source. Voltage controlled voltage source. This voltage, Vx, controls this voltage right here.
So like, okay, back to the minus 70 plus 2 Vx. You started from that 70 volt spot and you just kind of skipped it.
Yeah, let me go around the loop. I established that this is my loop direction, and my current is going around. I make a decision to say current is going around the loop this way. It's somewhat arbitrary. I don't know until I solve the problem. So I just guessed and said current is going around the loop this way. And everywhere I hit a resistor, current's going through this way, I say plus minus. Go through this way, I say plus minus. And now if I just go around the loop and watch the signs, let me write it again. Minus 70, because I hit a minus first, right? I hit a minus first. Plus, I'm just going to do Ohm's law, I times 10. Then I hit a plus sign, plus that voltage, which is 2Vx. But Vx is the voltage that's across here. So this voltage depends on that voltage. And then plus, I hit a plus sign first, plus 5I equals 0. It's the same thing I wrote here. I just wrote it in different order because I was trying to confuse everybody. So, and then I see that Vx, the voltage across this resistor, is Vx is I, my one loop current, times 10 ohms. And I put that, and I substitute that into there. So then I have minus 70 plus I 10. This is plus 2 times 10. Is that right? Yeah. 2 times 10 times I. That's what that is. Plus 5 equals 0. So minus 70 equals minus 70 plus I times 35 equals 0. And I come up with I equals 2 amps. Let's see, they didn't ask me what I was, they asked me what these voltages are. So I already said what Vx was. Vx is I times 10, right, from Ohm's law. So that's 2 amps times 10 ohms. So it ends up equaling 20 volts. Sure enough, it's 20 volts. And then VO, the way they've drawn it, if I was measuring, is in the opposite direction. So it's a negative sign of I times 5. So that would end up being negative 10 volts. So their markings there are how they're measuring it or how they're referencing it. So you had that one lab where everything was referenced to the black probe of the multimeter. So I got the two answers there. So Kirchhoff's voltage law is better for loop circuits because it's voltage around the loop equals 0. This one is better done with Kirchhoff's current law because everything's in parallel, which we defined what parallel is, and it turns out KCL is better for parallel circuits.
For the last one, you refer back to the polarity that they already had set for the resistor?
So when I give my answer, what is VO, I refer to the reference way they want to measure it. So it's like putting my black probe here and my red probe here. That's the way they want you to report it as, to measure it according to their reference system. But I'm telling you, if you're going to do KVL around a loop, establish your loop direction, and then put all your plus and minus signs consistent with that loop direction that you've drawn. Don't flip them around. Okay, so this one is going to be a Kirchhoff's current law, and I'm going to use KCL, and I'm just going to somewhat arbitrarily say that I into the node is a positive convention, and I out of the node is a negative convention. I can choose it either way I want, so basically I'm saying that if it's into the node, current is going into the node, it's positive. Current going out of the node is negative if I'm going to sum up all the currents. So if I sum up, in my little example, sum of the currents into the node equals 0. In this little case, I have I1 is positive minus I2 is 0. So, or in other words, to me it's often easier to say the ins equal the outs. Some sign. So current into the nodes equal current out of the nodes. So that's how we're going to do this problem. So where is our nodes? I have one big node up here. This is node A. And I have one big node down here. This is node B. There are two nodes in this circuit, and two and only two, right? Don't see any more nodes? Okay, good. So let's look at node A. Currents into the node equal currents out of the node. So 9 goes in. Anything else go in? I don't know what this one does, right? So I'm just going to pick one. I'm going to pick it there. I don't know. I'll call it, what do you want to call it?
Are you choosing if the current is exiting or entering?
Yeah, I need a current for this that's going through there. I2. I1. No, this is I0. We'll call this one I1 because it didn't have a name. Okay. So at node A, we have 9 goes in. Anybody else goes in? I have in, I have out, I have out, I have out. So 9 amps equals I0 plus this one is I0 over 4. This is a a dependent current source right there. The current that's right here depends on this current that's right there. That's why it has that equation. This value depends on that value. This value is always going to be 1/4 of that value. That's what it's saying. Plus what I called I1. So right now I have two unknowns there. I don't like that very much. Can we decide what this current is right here? We could. It's actually one of our unknowns. V out over 8, right? So I could put that in right there. What else do I know about this circuit that I can figure out? What is V out? Okay, so V out says it's the voltage across this resistor. What's the voltage across this resistor? This is a consequence of Kirchhoff's current law and things being in parallel. If something is in parallel, the voltage across them is the same, right? So this resistor is in parallel with this resistor. Can I redraw this circuit? I can redraw this circuit. Did I change anything in the circuit? If I reordered the components like that? I did not change anything in the circuit. Electrically, it's the same circuit. Why? Because all along here is still node A, and all along here is still node B, and it's like I took these parallel components and twisted the ends together. So I didn't change anything in the circuit when I do that. So all of these are in parallel with each other. So these guys are in parallel. If it's in parallel, the voltage here is the same everywhere, and the voltage here is the same everywhere. And we said that this voltage is V out between here and here. So this voltage between here and here is also V out, because I have V out between here and here, I have V out between here and here, I have V out between here and here, and it's the same between here and here. I can redraw this circuit one more way, just to convince you. Are you convinced now? So if I measure the voltage between here and here, voltmeter, the voltage is the same, right? So, okay, so if that is true, then we know that V out also equals Ohm's law, I out times 2 ohms. So we have V out, but V out is the same voltage as here, and that's I out times 2 ohms. So I can substitute that into this equation right here, and then we'll get down to only one unknown. So so I'm going to continue this over here. 9 equals I out plus I out over 4 plus I1, which was V out over 8. Correct? The voltage divided by the resistance. Next step, 9 equals I out plus I out, or I0 over 4 plus, right here, make that substitution, 2I0 over 8. So now I'm finally down to one unknown. Go away. One unknown. So 9 equals I out. 1 plus 1/4 plus 1/4. And then solving, I will get I0. I keep calling it out because a subscript 0 is often used for out. So I0 equals 6 amps. Oops, what did the problem ask for? Problem asked for I0, 6 amps. Yes, I got it right. And it asks for V out. So V out equals I1. V out equals I1 times 8 ohms. And oops, that's not what I wrote that wrong, didn't I? V out, I said right there, is the same everywhere, is I out times 2 ohms, right there, which is the same thing, different current right there because it didn't ask me to find that current. But I know that V out is I0 times 2 ohms. So V out is 6 amps, 2 ohms, which equals 12 volts. Yes. So, one more for today. Is this helpful? I hope. Good. Okay, this problem, it's not so obvious what to do, whether it's to use KCL or KVL when I look at this problem. Because I see some things in series. Aren't these in series? These two things are in series. These two things are in series right here. And so it's not real clear to me which way is the best way to approach this problem. So When I'm not real sure, I write down things that I know about the problem first by looking at the problem. By the way, these are problems from your textbook, but they don't tell you how to solve it. They give you the answer, but they don't tell you how to solve it.
So when everything is in series, you can say KVL, but when some stuff's in parallel, it can be either or.
When it's in parallel, KCL. If it's pure parallel, like the one we just did, KCL. If it's KVL, it's a pure loop. If it's a pure loop, single loop, it's KVL, clearly. If it's mixed like this, you got to like pull all your tools out of the hat right now. So this problem is a mixed problem. And before I decide how to do it, I usually like look at it and see what do I know. And my hints is that they wrote these currents for like doing KCL, right? But can I say what these currents are? I actually can. So I1 equals, if I'm going to say Ohm's law, it would be V over R, right? So I1 is the voltage across the resistor, voltage 1 over 2 ohms. But it turns out I can know voltage 1. I'm going to make a definition right here. I'm going to call this node voltage at A to help me out. So if I somewhat arbitrarily call this my 0 reference point, I can call anywhere my 0 reference point, but it's usually easiest at the bottom of the circuit like this, and it's kind of conventional to draw it that way. If I do that, I'm at 0 volts here. I come up 10 volts right here, and I know that this point on the circuit is at 10 volts. I can also do the same thing here. I'm at 0 volts down here, my reference point, and I know that this is 6 volts lower than that reference point, and I know that I'm at minus 6 volts right here at that node. So I actually have some node voltages known right there. I don't know this one right now. There's no way I can know VA. But, so continuing this, I1 is the voltage across this resistor divided by the resistance. And I know that the voltage across this resistor is 10 minus VA, 10 going this way. Okay. I also know that I2 is this one right there, is my node that I called VA minus 0. So VA minus 0 over 8 ohms. And I3, can we write I3? So watching my conventions, current going into the resistor is plus minus. Watching my conventions there, it is VA minus 6 over 4 ohms. Okay? So everything's in terms of that VA right now. I didn't solve for anything. So I'm going to take the hint and do KCL at that node. That's what I'm going to do. And I'm going to say the current in equals the current out. And then I'm going to go ahead and substitute my relationships in here. So 10 minus VA over 2 equals VA over 8 plus, and VA minus 6 is VA plus 6, right? Over 4. And then it's a matter of doing the algebra. This is how I did the algebra. I wanted to get rid of my denominator, so I multiplied everything times 8. And then when I do that, I'll get 40 minus 4 VA equals VA plus 2 VA plus 12. You can check my algebra if you want, but I got the right answer, so I think I did my algebra okay. And then 28 equals 7 VA. VA equals 4 volts. So I found the voltage at that node. Everything's in amps, everything's in ohms, everything's in volts. Nothing complicated there with my unrealistic numbers, because they're usually not nice numbers like this. So I have VA. That means I can come back over here and find all of these currents, because I had those relationships. So I1 equals 10 minus VA over 2. So it's 10 minus 4 over 2, which equals 6 volts. I1 is, 6 amps. I1 is 3 amps. Because I can't do the math. You're supposed to check my math. 10 minus 4 is 6, divided by 2 is 3 amps. Yep. I2 equals VA 4 minus 0 over 8, which is 0.5 amp, which is 500 milliamps. I2 is 500 milliamps. Yes, yes. I3 is VA plus 6 from my relationship over 4, which is 10 over 4, which is 2.5 amps. And your textbook has it wrong, and I marked it wrong in my notes. Yes, your textbook has it wrong. So I3 was actually 2.5. Right? 4 plus 6 is 10, divided by 4 is 2.5. Yes. What else did it ask for? What's V1? Voltage 1 is the voltage across here, which is 10 minus 4. So voltage across 1, 10 minus 4, which is 10 minus VA. So it is 6 volts. Correct. And what else does it ask for? Voltage 2. Voltage 2 right there. Voltage 2 is I2R2. That's the only way I can get it. I2R2 is 0.5 amps times 8 ohms is 4 volts. Interesting they had that right. Oh, and then finally voltage 3. Voltage 3 is VA minus 6. But you could also do, what else could you do? You could do VA minus 6. That would give you voltage at 3. You could also say it's I3 times 4 ohms, and you should get the same answer, right? Either one's okay. I mean, it would give you, let's check. VA minus 6 is 10 volts. 10 volts. And I3 times that resistor, since they got I3 wrong, would be 2.5 amps times 4 ohms. Hey, guess what? It is 10 volts. So either way, you can find V3 by I3R3. Actually, all of them you could just do Ohm's law. V1 could have been I1R1 also. I would rework these problems for yourself also, because there's a lot of concepts playing all at once in these problems, and that's what makes them difficult. So textbook had a wrong answer there. It was 2.5 amps. Next slide talks about series resistors. I'll tell you right now, series resistors just add up. Total resistance right now is this plus this plus this. If I put my voltmeter right here, measure the ohms, I will get 14.4 volts. Simple enough when you look at it. It is a consequence of, a result of, Kirchhoff's voltage law, that the resistors add up, and I'm going to show you how. So if I apply there's a voltage here. If I apply Kirchhoff's voltage law around this loop right now, I would say minus V equals I times 4 plus I times 2.4 plus I times 8. That would be, plus V, because I wrote, if I said minus V, it would be minus V plus 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 equals 0, but I moved the sources up to the other side, right? I could have said minus V equals I 4 plus minus V plus I 4 plus 2.4 plus 8 equals 0. That's Kirchhoff's voltage law. So rearranging the terms, I got it in that kind of form, and I get that V equals I times the sum of all the resistances. So this V, you can say that that's equivalent to an I times R equivalent, which equals I times sum of all the resistances. So you use Kirchhoff's voltage law to prove this relationship, basically. So resistors in series add up. Resistors in parallel. Resistors in parallel obey this equation. It's a result of KCL. Surprise, surprise. So here the book nicely put the voltage source on there. So there's one total I going out, I1, I2. So I say I equals I1 plus I2, which equals V over R1 plus V over R2, which equals V 1 over R1 plus 1 over R2. And you can kind of see that if I had more and more resistors out here, it would just change the form of this equation, right? So on the equivalent side, if I were to do that as one equivalency, it's equivalent V over V over R equivalent equals V 1 over R1 plus 1 over R2. Sorry. Did I just screw that up? Yes, I did. I was supposed to say I times R equivalent. Oh, screw up on my part. It's not. I had it right the first time. Yeah. Then you cancel out the V's. 1 over R equivalent equals 1 over R1 plus 1 over R2. And if there's many resistors, it's pretty easy to see that it would extend itself. When there's shortcut, when there's only two resistors, you have 1 over equivalent resistance, total resistance, equals 1 over R1 plus 1 over R2. Multiply everything times R1 times R2. I get doing the algebra. It's continuing to rearrange the terms. Cancel, cancel. R2 plus cancel, cancel. R1. Multiply both sides times R equivalent. This will cancel, and I'll have R1, R2 equals R equivalent R1 plus R2. And then you get R equivalent, the equivalent resistance is R1, R2 over R1 plus R2. It only works when there's two resistors. So if I see two resistors in parallel, I can immediately write that the equivalent resistance is this equation right here. So this is like, go away, this is like saying, equivalent resistance is like saying, I have my voltage source and I have one equivalent resistance right there. So you can take these two resistors and replace it by one equivalent resistance. Likewise, in the series circuit, I can have my voltage source right here. And instead of having three resistors in series, I could have one equivalent resistance of 14.4 ohms. So I can replace my three resistors in series with one. Here I can replace my two resistors in parallel with one, and that's the value of it. This is going to be useful when we simplify circuits. Like this one. This is the last one that we're going to do today. I have more example problems for Thursday because I think showing the examples helps you. It says basically find the total resistance of this. So I want this circuit to be replaced by one equivalent circuit, R equivalent. Some people say it's R total. I think the EE211Cht2pt2 textbook uses R total a lot. So this is called a ladder network, by the way. So I want to replace the ladder network with one resistance. What is the total resistance there? So if I'm measuring from this end, you're going to start from this end. And you're going to look for series and parallel combinations and simplify as you go. So the first thing I see is that there's three resistors in series here. Agreed? So if that's true, I'm going to redraw my circuit. And I'm not kidding. Redraw, 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 or you will mess up. 4, 6, 3 hasn't changed. 3 hasn't changed. 4 hasn't changed. But what I did change is this. I found a total resistance for that, right? Which is 9, 10, 11, 12, 12. Now, I can replace that series resistor with one resistor. I could put it here. I could put it here. I could put it here. It doesn't matter, does it? So this now became a 12. So that was step one. Now what do I look for? I'm still working from the right to the left here. I see that these two guys are in parallel. 4, and then we write like this. 4 is in parallel with 12. It's only two resistors, so I can say it's this times this over this plus this. That little shortcut I just told you about. Which turns out to be 3 ohms. 12, 24, 36, 48, 48 divided by 16. Yeah, 3 ohms. So that's what this turns out to be. I redraw my circuit. 4, 6, 3, 3. And the part that I just did is now a 3. Correct? So, okay, I redrew it again. Now I look at it again and I see these guys are in series. Pretty easy. 4 is still there. 6 is still there. 3 is still there. And that is 6. Correct? Guess what 6 in parallel with 6 is? Yeah, it always just halves it. 4 is still there. This is now a 3. And this is now a 3. It always just halves it. So now I just have left with 3 things in series. 7, 8, 9, 10. 10 ohms. Don't have the answer for that one. I got 10 ohms. Okay.
I have a question.
Yeah.
As far as showing your work, if you can just like do something like that in your head, can you just go from that circuit to like a circuit where it just shows one 10 ohm resistor, or do we have to show every single step?
You don't have to show every single step, but when they get more complicated, it's helpful to draw out the paths. Yeah. So I don't know. And some of the big problems, it's easy to mess up if you don't draw each step. So, and I think that's the last one we're going to do for today. Yeah, because this one's a little ugly. I didn't like this problem very much because it wants to do everything. See, it's in conductance, right? 1 over resistance is conductance, and conductance is in units of Siemens. But sometimes, like if I have R1, R2, I'll do this problem on Thursday, R3. I say I have 4 resistors in parallel, right? They're in parallel. What's that total resistance? You have to do this ugly equation. And and do all of that and invert in the end, and you'll get whatever that total value is, right? So when it's all in parallel like that, what is this? This is conductance of 1, conductance 2, conductance 3, conductance 4, and that is conductance total. So in parallel, it's easy just to say for parallel, conductance total is conductance 1 plus conductance 2 plus conductance 3 plus conductance 4. And so that's what we're going to use on that problem, but I'm not going to do it with 3 minutes left to class. But I will do this problem next time. Hopefully that helps you some with homework.